Hi, in this video I'm continuing with Graph Neural Network series, and I'll be covering this paper called Inductive Representation Learning on Large Graphs, or also known as GraphSage. So basically the main proposition of GraphSage is that they developed a method that's inherently inductive and can work on huge graphs. So the later paper that came after GraphSage is SpinSage, and I'll be covering that one in one of the next videos. And this is basically a precursor to that paper, which is really awesome and has an awesome implication as a recommender system in Pinterest. So basically they say here, most existing approaches require that all nodes in the graph are present during training of the embeddings. These previous approaches are inherently transductive and do not naturally generalize to unseen nodes. So let me do just a quick recap of how those methods basically work. So what you have is you have a static graph. So let's draw some toy graph here, and I'll be using this one throughout the series. And basically what you're trying to do is you're trying to train the embeddings for all of these nodes. So basically an embedding table, and this one has dimension n. So this vertical dimension is n, where n is the number of nodes. So basically this. And this dimension is d, which is a hyperparameter, and is usually something lower dimensional than the input feature vectors. So all of the nodes have features associated with them, and we want to find a lower dimensionality representation of those nodes, which would encode both the features and the neighborhood information. Now the problem with these methods is that, so they would basically what they did is, so if you have, for example, this node and this node here, you want to make those two embedding vectors as similar to each other. So if we just represent those vectors in 2D space like this, we want to have 1 and 2 close to each other. And on the other hand, if we have some nodes somewhere further away connected via some intermediate node with 1, and let's call it maybe 3, and maybe it's somewhere here in the table, so we want to make it be dissimilar to those two vectors. Okay. So what's the problem with this approach? So the problem is, once you train this embedding table, it's really hard to generalize to new unseen nodes and to new graphs. So let me draw it like this. So basically, let's say this thing, we pack it up into this blob and we call it G1. And if you want to add new node, or maybe even 2 new nodes, you basically have the following. You have this table, which was previously trained and has meaningful vectors, and you just append 2 new vectors here, which are initialized randomly, because we still don't know anything about those, and we have to train those. So now there are a lot of problems with doing this, and I'll address some of them later, but it's basically even harder once you want to generalize to unseen graphs, because this graph 2 here has totally different random walk statistics than this graph here, and so this embedding table won't make any sense if you try and just use it here. So you'll basically have to retrain the whole thing, or find some way to kind of align nodes between these two graphs, and it's in any case it's cumbersome, and we'll now see what GraphSage did. So basically they said here, instead of training individual embeddings for each node, we'll learn a function that generates embeddings by sampling and aggregating features from a node's local neighborhood. And GraphSage is not super different from GAT or GCN if you looked at my previous videos, but but there are some differences which make it more like generalizable to large graphs and more efficient than GAT and GCN. Now I'll show you why. So by the way, GraphSage. So the Sage part is just an acronym from sample and aggregate. And let's see those 2 steps. I'll just first start high level, and then I'll have a pseudocode, and I'll explain in detail how the algorithm works. But basically what we do is, instead of taking the whole neighborhood, as we did with GCNs and GATs, we basically just do a uniform sample from the neighborhood, and then we repeat that after through a couple of GraphSage layers, and we end up with this. So basically this red node in the middle will end up having some parts, like some mixture of representations of these orange nodes. And basically these aggregate functions are trainable, and they're general here. So the paper itself suggested a couple of different variants, and we'll see those in a minute. But if you remember, so basically what GCNs did, they would just simply do add these up, but they would be normalized by 1 over square root of di dj, where those are the degrees of corresponding nodes. And GAT did this via attention, so it dynamically figured out these coefficients with all of these representations, and then it would just multiply them and add them up. So that was just a high-level overview, and I'll slowly start digging into depth. But let's start with some related work. Basically, before GraphSage, there was a couple of methods that did similar things, and Planetoid, Inductive, I stands for Inductive, version of Planetoid, did something similar, but the difference is it only used the graph structure during training, whereas GraphSage and GCN and other spatial methods actually use the graph structure during the inference time, and that makes them different. And also they later so GraphSage in a way generalized the GCN algorithm to an inductive setting. And so they say here, the original GCN algorithm is designed for semi-supervised learning in a transductive setting, and the exact algorithm requires that the full graph Laplacian is known during training. And yeah, a simple variant of our algorithm can be viewed as an extension of the GCN to inductive setting. And we'll see that in a couple of minutes. And this is the pseudocode for the GraphSage algorithm. It's if you're familiar with GCN and GAT, they have a really similar structure. Let me try and go through this pseudocode and make some sense out of it. So first, the notation. So they have a graph G that contains these sets of nodes and edges. They have initial node features, and which are like problem specific. Maybe if we have a citation network like this, maybe those node features would be, let me connect them somehow, maybe this paper cited these 3 ones. So these node features would maybe correspond to, you take the abstract of the paper, you just apply word to back to every single word, you just do some bag of words, and so you basically average them out, and you maybe add some additional information like the node degree. So this one has 3, these ones have 1, etc. You just append the node degree here, and you append the abstract information here, and that would be a particular node feature. So those are these axes. We have depth, which is basically the number of layers in GraphSage, and we have these weight matrices, WKs, which are trainable, and so those will be trained during the unsupervised and supervised training process, and I'll show those in a couple of minutes. We have, nonlinearity, sigma, and these are important differentiable aggregator functions because they are also trainable. So WKs and these functions are something that we'll want to train. And finally, we have this fancy notation for neighborhood function. This is basically the power set of V. So this is basically just a fancy way of saying maybe node 1. So this is maybe node 1, 2, 3, 4. The whole power set would have 16 elements. So the empty set, you'd have the particular nodes, then have the tuples, you have the triples, and finally you have the every single node. And basically one particular mapping could be 1 maps to 2, 3, 4, and that's the particular scenario we have here. So 1 gets these neighbor. These are the nodes that are neighbors of 1. Okay. And let's see how the algorithm itself functions. So basically, we start by initializing these representations with initial node features for every single node in the graph. And later I'll show you the mini batch version they have, and that's really important because they want to use this algorithm on huge graphs, like maybe the graphs which have like billions of nodes. So you don't want to have to iterate over every single node in the graph. You want to have just iterate over subsets. But the idea is very similar. So we iterate over every single layer. So we iterate over different graph stage layers, and for every node in the graph, we do the following. We basically take the neighborhoods. So in this particular case, for node, this would be maybe node V, and these are the neighbors, and we just aggregate those representations. So now aggregate can be a bunch of things, and we'll get to that in a moment, but it's basically either mean, maybe you can use LSTMs, you can use max pooling, bunch of different stuff, but basically you have a way to somehow take these representations and combine them, aggregate them. Once you have that, you just concatenate the current representation, so the current node's representation. So we are currently at V, and this is V. So we take its representation and we concatenate it with the aggregated representation, and we just do a feed-forward layer, and that's it. There is one additional detail. They just do this normalization step, which basically makes these vectors unit norm, which makes them lie on the unit hypersphere. And now hypersphere is just a fancy name of saying like sphere in higher dimensions. So basically, if the number of dimensions in these representations was 3, we would basically have a 3D sphere, and these vectors would lie somewhere on that sphere. And we just repeat that over a couple of layers, and that's it. We get the final representations, which are denoted as ZV. So now, once we have these representations, how do we train GraphSage? And it turns out they used two approaches. We can either train GraphSage in an unsupervised manner. Let me just, here. So we can either train it like this. So basically, if you're familiar with graph embedding methods, which I mentioned, we want to make sure that these, the nodes that are close to each other, that are connected, have similar embeddings, similar representations. And on the other hand, we want to have these nodes which are not connected in the graph have very dissimilar representations. And I'll try and help you out let's just parse this equation. So basically, sigma here is nothing but a sigmoid function, which looks like this. Basically, we have 0, 5 here, and in the limit, it approaches 1. So this is sigmoid's limit. And so basically here, once you do a dot product between two node representations, so let's say we have a graph. We have a graph like this, and maybe not all of the nodes are directly connected. And let's take this tuple here. So because they are connected, we want their representations after we do a couple of iterations through the GraphSage, we get the final representations, and we want those representations to be as close to each other, because once they are really close, so once those vectors are really close, this value gets really big, and sigmoid from a big value gets closer to 1, and log of 1 equals 0. So that means we are minimizing the loss function, and that's something we want to do. And then we have this part of the equation where we do a similar thing. So maybe we take this node, this is the negative sample, and we want these two nodes to be very dissimilar. So what we do is we want to make them as dissimilar, because once they are really dissimilar, they'll get really negative, and because of the minus here, they will be really positive, and that means the loss again gets pulled down to 0. So and we have this Q factor, which is a hyperparameter, and it determines how important it is to have these minimized down to 0. So that's how the unsupervised method and learning procedure for GraphSage works. And they see here a generator from features contained within a node's local neighborhood rather than training a unique embedding for each node. So the difference between graph embedding methods and GraphSage is that we don't have a embedding table here. So we are not training those fixed tables which are not prone to being later used in an inductive setting. We are training those WK matrices, and we're training those aggregate functions, which we'll see what exactly they are in GraphSage in a minute. GraphSage can also be trained in a supervised manner, and for example, if you have a classification task, it's just you just figure out the representations, you do pretty much cross entropy, and you train those WKs and those aggregation functions. So I won't get into much details there. An important thing about GraphSage is that once we have, so if we have a node, and we have some huge neighborhood, maybe some of these networks have like maybe over 1,000 neighborhood nodes. What they do is they never, in contrast to GATs and in contrast to GCNs, they never sample, they never try and aggregate all of the neighborhoods. They just subsample. Maybe they use, in particular, they used 25 on the first layer neighbors, and they used 10 neighbors in the second layer of GraphSage. And what that means is, in the first layer of GraphSage, you basically take only uniformly sample and take 25 neighbors, and you aggregate those representations only. And in the second layer, you'll just take 10, and that means you're basically that means that this node here will basically potentially see up to 250 different nodes. Okay, where was I? Here. And they mentioned that here, so we're using overloaded definition. We define the neighborhood as a fixed size uniform draw from the set of those edges. So from all of these neighbors, from the full set, from the full neighborhood, and we draw different uniform samples at each iteration. So that means this node will have, for every single layer of GraphSage, will have different neighborhoods picked up. So it's stochastic. And yeah, they mentioned here also, so they usually use the product should be less than 500, so to just have this trade-off between the performance and between the efficiency of this algorithm. So now let's jump to those aggregator architectures, and they're using basically three different architectures. So one is the mean aggregator. So that means once you take, once you sample some maybe 25 neighbors, you just do element-wise mean, and then you concatenate that representation with this node feature vector, and you do the feed-forward layer, right? So that's one way how you can aggregate, and that's the dumbest way, pretty much. The second way they propose is similar to GCN. So they ditch the concatenation altogether, and they just take all of these. So they take the neighbors, the sample neighbors representations. They take this representation, and they do a mean over all of those. They don't have any concatenation. So that means this particular aggregation, this method, they call it GraphSage-GCN because it's similar to GCN. Other than the normalization constants are not the same, and they mentioned that here. So this differs from Kipf. Kipf is the author of GCN, exact equation by minor normalization constant. So if you remember, GCN had this 1 over square root di dj, which are basically degrees of these nodes. So this node has some degree, and maybe one of these neighbors has some degree. So once you combine those two, you normalize them with this constant. Whereas here, they don't do that. So yeah, they mentioned here an important distinction between this convolutional aggregator and our other proposed aggregators is that it does not perform the concatenation operation in line 5 of algorithm 1. So that means here, if you remember, so they just don't do this concat part. They just aggregate all of these together. That's the difference. Whoops. Okay, so that's the mean aggregation function. Now, they also tried and used LSTMs, and now the problem with LSTMs is that they are inherently sequential, and they are ordered. So that means basically they had to find a way how to use LSTM as a symmetric aggregator, and what they did is they just applied random permutations to know its neighbors. So once you have the neighborhood, you just do some random permutation, and then you just find the aggregation doing the following. So basically, if you're familiar with LSTMs, if you're not, I'll just link a really good blog from Christopher Ola, which could help you understand grooves and LSTMs. So basically, it's initialized, LSTM is initialized with some random H0 state, and you would input the first node representation. I'll call it maybe V1, whatever, and then you'd have some new state here, and finally you'd output the second neighbor from the current permutation, and anyways you end up with a final aggregated representation that combined all of the previous node features. And that's how the LSTM aggregator works. So those parameters inside the LSTM would be trained together with those WK matrices, and those are all of our learnable parameters. Finally, they have this max pooling aggregator function, and what they do here is they just take the neighborhood again. So they take those representations, they take some subset of those representations, and they just apply a feed-forward neural network here. And so once we have those transformed features, they would just do an element-wise max pooling. So basically this approach is inspired by this PointNets paper. And in a nutshell, the PointNets paper showed that this max pooling worked really well for them, even better than doing mean pooling or doing attention-based poolings. So in a nutshell, what this paper did, it works with point clouds, and it starts with maybe n points, and every single point has 3 features, and those features are just the coordinates x, y, z. And once you do some transforms and MLP transformations, you end up with this n, where n is number of points, and you have 1024 features. And they just did they just do element-wise max pooling. So that means whatever the max element in this column is, that will be put here, and then you do the same for every single column. And as I mentioned, they tried also doing the mean of this column, and they tried doing the attention. So the attention, what the attention does is you basically find coefficients for all of these vectors, rows. So you'll have maybe alpha 1 for the first row. You'll calculate all of those alphas. You'll finally have alpha n. And now what we would do is you would basically just multiply these corresponding row vectors by alphas, and that's how you'd aggregate, and you'll get the global feature finally. So that's pretty much everything you needed to know about GraphSage, aside from that detail about how did they do the mini batch part, and I'll explain that in a couple of minutes. But first, let's just go through the experiments. And as I previously said, the main advantage of this paper is that they're really good at inductive setting, and they use this PPI protein-protein interaction dataset, and there they have these entirely unseen graphs, which is something that's really challenging for all of those graph embedding methods, and for all of those previous methods that were inherently transductive. As I already mentioned, they used sampling sizes of 25 neighbors in the first layer, 10 in the second layer. And one more detail is that in the multigraph setting, they can't apply deep walk because of this fact. So in the multigraph setting, we cannot apply deep walk, since the embedding spaces generated by running the deep walk algorithm on different disjoint graphs can be arbitrarily rotated with respect to each other. And I'll touch on that a bit later, but just for now, just keep that in head that those graph embedding methods are really hard to generalize to inductive setting. Okay, let's see the results. They had 4 baselines. The random classifier, they just used the raw features. So those are those, I mentioned those, maybe you have the abstract here, you have degree information, and that's your feature vector. And here they just use those raw features and maybe just do some MLP on top of those, and that's how they learn to classify without using any graph structure information whatsoever. On the other hand, they had deep walk, which was trained a bit smarter. Basically, it encodes the graph structure as well, and here is a combination of doing both of those. And then they have 4 different graph stage algorithms depending on the aggregation function they use. So we have GCN, we have mean, LSTM, and pool, and here we can see it pretty much steadily increases here. And also they have the unsupervised trained graph stage, and they have the supervised trained graph stage, and you can also expect that this will increase, and it did. So what we can see here is that basically, yeah, they got better results than all of those baselines. And now there is the best aggregator functions seem to be LSTM and pooling, whereas pooling is a lot cheaper, so they finally gave it a slight edge, and they said that the pooling had the best performance altogether. It's probably the best overall because it has the best trade-off between the performance and the efficiency. Yeah, here they just in this chart they just showed that these graph embedding methods such as deep walk have really high cost to do the inference on the full test set, because they have to recalculate, to retrain those embeddings, and that's really computationally costly. And this is log scale here, so that's 1,000 seconds. That's much more than what Graph Sage takes. They also have a small chart here where they plot how the performance, so the F1 score, and how the runtime increase as we increase the sample size. So if you remember, we had 25 and we used 10, and here they just experimented. They went all the way on up to 75 neighbors, and we can see that the performance does increase as well as the runtime. So empirically, they just figured out that some smaller neighborhood sizes such as 25 and 10 are performing the best overall. Okay, that was pretty much it for this main part of the paper. Yeah, they mentioned here that so GraphSage LSTM is significantly slower than GraphSage Pool, so approximately twice, so perhaps giving the pooling based aggregator a slight edge overall. One more interesting theorem here, and they have a whole proof for this thing that's like 4 pages long, and I won't get into the mathematics in this video, but I just want to briefly explain what they said here. What they say here is that GraphSage, even though it heavily relies on features and like aggregating those features and stuff, it understands the graph structure really well. So how they proved that is the following. So they showed that the final representation, so ZVs, if you remember from the pseudo algorithm, can be made like arbitrarily close to these CVs, which are basically something called clustering coefficients. And I'll now explain what those are. So this equation again tells us that we can make the representations arbitrarily close. So whatever epsilon you give me, no matter how small, like maybe you give me 0.01, I can make the ZV close enough to the real clustering coefficient. So what's the clustering coefficient? Basically, if you have some small graph here, something like this, and let's say this node 1 is connected to these 3 nodes, basically the clustering coefficient, let's call it C for node 1, is if these are all connected together like this, so they form a clique, then the clustering coefficient equals 1, because the neighborhood nodes have the highest connectivity pattern that's possible, and that's a fully connected graph. So if we were to just disconnect maybe these two edges, we'd be left with this one, and the clustering coefficient would drop to 1/3. So basically what they state here is that the graph sage can learn all of these, this is like a structural information in the graph, and they can learn it to an arbitrary precision. Okay, let me wrap up this paper explaining the mini batch part and something related to graph embedding methods, which will be interesting. Basically, the main part, the only difference is this. So we won't be iterating over every single node in the graph, because the graph can be really huge, like maybe a couple of billion nodes. So basically they calculate these B sets. So if we have, let's assume we have 2 layers in graph sage, that means they'll be calculating set B0, set B1, and set B2. And let me try and illustrate what those are and how they look like. So basically, if we have some huge graph that has a couple of billion nodes, maybe we're only interested in representations of a small subset of nodes, which we'll call B2. Now, because of the way how graph sage works, it just aggregates the neighborhood of every single node in a particular layer. That means we'll need one hop neighborhood of the nodes in B2, and let's call that B1. And now, because we have 2 layers, we'll also need the one hop neighborhood of B1, which is basically B0. And that will be a superset of B1, which is itself a superset of B2. So this is what the algorithm would put in these B sets. So let me just zoom in a little bit on this one. So we start with so these are the target nodes that we want to calculate the representation for. And so we initialize B2 with that one, and then we start going towards 1. We initially initialized B1. We initialized it with B2 nodes, and then we iterate over B2's nodes, so over these nodes, and we just add up. We just do a union of all of the neighbors of all of the nodes in B2. So we'll go through nodes, and maybe some of these nodes will have neighbors that are here, and thus we'll slowly build up B1, and then we'll slowly build up B0. And then in the main loop, what we do is we first initialize the initial representations with feature vectors coming from B0 set. So we'll only need to think about B0 vectors. We don't have to care about any of these nodes. So we gain efficiency. And so now the algorithm, what it does, we start with B1. So we start with these nodes. So we iterate over those nodes, and we do aggregations. Some of them will belong to B0, and luckily we already have those in memory, and we have those feature vectors, so we can calculate all of the representations in B1. And once we have B1, in the next cycle, once k gets to 2, we'll be iterating over nodes in B2, and we'll be building up representations, and we'll luckily have all of these representations calculated from the last iteration. So we can finally have all of the representations that we're interested in B2 calculated and put into ZUs. And that's pretty much it. That's how the mini batch algorithm works, and hopefully that was clear enough. If you have any questions, please comment down in the comment section. I'll try and answer all of them. And yeah, one interesting thing is they sample with replacement in cases where the sample size is larger than the node's degree. So maybe we have a node and it only has maybe 3 neighbors, like this. But if you remember, S1 was 25 and S2 was 10, which means we'll have to repeat some of these features before we call the aggregate function. So maybe we'll have 8 of these, we'll have 8 of these, and we'll have 9 of these, and then we'll call the aggregate function. So that means sampling with replacement. So yeah, that's a small detail. And this is one more interesting detail. And as you can see, GraphSage is all about these small details which are making the implementation a lot more efficient, and it can later be used on huge graphs. And here what they say is basically they do a pre-processing step on these huge graphs, and in case some of the nodes has maybe 1,000 edges, they'll just subsample up to 128 of them. So every single node will have its degree less than or equal to 128. And they say here, due to heavy-tailed nature of degree distributions, we downsample the edges in all graphs before feeding them into the GraphSage algorithm. In particular, we subsample edges so that no node has degree larger than 128. The final thing I want to mention is the part that I mentioned in the beginning, and that's what's the problem once you're dealing with these embedding tables. So basically, what you're doing by doing those, trying to make some vectors similar and some dissimilar, you're basically doing implicit factorization. So basically, you're trying to calculate that Z matrix, and this is number of nodes. This is the hidden dimension D, and if you do transpose this Z matrix into ZT, and you just do multiplication, what you end up is this matrix M, which basically contains all of these similarities between vectors. So you'll have how similar vector 1 is with vector 1, and you'll have how similar vector 1 is with vector 2, etc. So you have a huge M by N matrix, which basically tells you how similar or dissimilar those embedding feature vectors are. And you're basically, by doing those random walks and training those graph embedding methods, you're implicitly trying to find this implicit M matrix, which contains the random walk statistics. And now the problem is that, as you can see here, you can basically have a whole family of these Z matrices, which basically add up to M. And that means those embedding vectors can rotate. The whole space can rotate, and you'd still have the same matrix M. So now why is that the problem? So the problem is once you try to add new nodes to your graph, as we saw in the beginning. So basically, if you try and you have graph G1, you have embedding table for G1, and you try to add maybe 2 new nodes. And what happens is you'll have to update the table. And if you just do the following, so basically you had this table previously, and now you're trying to add 2 new vectors. But the thing is, you train a classifier for those vectors here, so you have some classification head here, which was trained for those. And once you add up these 2 new random vectors, and if you try to retrain everything, then these won't be working correctly with this classifier anymore, and you'll mess up everything. All of the training will be pretty much in vain. And so yeah, they mention it here. Moreover, if we update all embeddings during training, not just for the new nodes as suggested by DeepWalk, then the embedding space can arbitrarily rotate compared to the embedding space that we trained our classifier on, which only further exacerbates the problem. So basically, once you add, again reiterating, once you add new nodes, if you just do this naive retraining, you'll mess up the classifier, because all of these will start rotating, because as we already saw, all of those families still add up to this matrix M. And they suggested here a couple of reasonable approaches. So some reasonable approaches to alleviate this issue of statistical drift are to not update the already trained embeddings when optimizing the embeddings for new test nodes. So that means we pretty much freeze up all of these. So we freeze them up, we don't change those. And second, to only keep existing nodes as context nodes in the sample random walks, i.e. to ensure that every dot product in the skipgram objective is a product of an already trained node and a new test node. So that means once you're doing those random walks, you only take context nodes from these that are already trained. So you can take, for example, if this is a new node, let's call it node number 3, and this is also a new node, and even though this node 3 is on this random walk, because it's a new node, we won't be using it as a context node. If you're familiar with how the word2vec and these graph embedding methods work, you'll understand what I'm talking about. And so basically the second approach, the second suggestion they have is only use nodes that are already trained as the context. There was a lot of information packed in this video. I think it's worth just comparing GraphSage with GAT and with GCN, because all of the three are spatial methods, and GAT and GCN are the most cited papers in the GNN literature. So the structure is really similar if you take a look at it. So we have a node and we have a neighborhood. And what GCN and what GAT do is the following. They just aggregate all of the node features, and before they add them up, they just scale them with a certain coefficients. So basically GCN takes this 1 over square root di times tj, which are the degrees of those nodes, and so we take both the neighborhood features as well as the current nodes feature, and we just scale them with this. That's GCN. And what GAT does instead is just computes dynamically these alpha coefficients, which are just attention coefficients, and then multiplies those nodes with these coefficients. That's GAT. Once you multiply them, you just add them up, and then you do a simple projection followed by a simple nonlinearity such as ReLU. So you have this, let's call it aggregated features, whatever, and then we just take those, we project them, and we do nonlinearity such as ReLU. On the other side, what GraphSage does is it doesn't take the full neighborhood, it takes a subsample, uniform subsample of the neighborhood, and it again aggregates those features in a bunch of different ways. Some of them you saw, like mean, you can do LSTM aggregation, whatever, and finally you again do projection and followed by a nonlinearity. So the pattern is really similar. GraphSage is a bit more efficient because it subsamples the neighborhood, and it experimented with different aggregation function and also some of the other details you heard during this video. So that was it. If you found this video useful, I'd really appreciate you leaving some feedback in the form of a comment in the comment section. That will help me like twofold. First thing is I'll get much better by reading your feedback, what I'm doing right, what I'm doing wrong, and secondly, you'll boost these videos like because of the way YouTube algorithm functions. So anyways, if you found this video useful, consider subscribing and consider hitting that bell icon if you want to get notified for every single video I make. And yep, until next time, keep learning deep.